Could basalt flow rock structures really have been left behind by giant trees? Let's see what we can uncover about the true origin of these columns. Now, in order to answer this question, let's clarify exactly what mystery we're trying to solve here. The root of our curiosity can be mostly summed up by one clearly worded question. Are these structures organic or geological in origin? Let's begin by covering some facts about these basalt columns. Here we will observe and analyze these various rock formations as they appear before us at this point in history. We will not be making claims based on conjecture as many others have. Evidence will be, and must be, at the heart of our research. So, what do these structures have in common? These rock formations and others like them have been chemically analyzed to reveal they are composed predominantly of magnesium, silicon, and calcium oxides. They also contain small amounts of other oxidized elements like potassium, sodium, iron, and titanium. These elements are found in most rocks but fall within a much more narrow ratio in igneous-type rocks such as basalt. Make a mental note, this will be important later. Interestingly, these elements are commonly found together all over the Earth, but grinding individual chemicals up and mixing them together does not form strong rock. Turning raw elements into basalt rock is a process that takes some oxygen and lots of heat. Intense heat must be applied in order to melt the elements together so they can mix evenly and completely as a liquid. It is this even distribution of elements that allow the rock to stay strong as it cools. If the elements are unevenly distributed, the rock is more likely to crack and shear at random angles as it cools, resulting in weak formations which will more quickly become inconsistent piles of rubble as water erodes their structures over time. But we're not just talking about mountains here. What about these beautiful hexagonal structures? What can their chemistry and structural properties tell us about how these columns were formed? Do the fractures and shards of these hexagonal columns reveal anything that can help us understand more about their history? Identifying how the columns are structured is very important to understand what caused them. If material color and hardness are even throughout the column, it would demonstrate that the columns are composed of thoroughly mixed elements. If this is true, we would expect these columns to behave in a similar way to other contiguous hard materials. Hard materials tend to crack rather than shatter or crumble. Thermal stress, such as rapid cooling, can cause some contiguous materials to develop a grain and become hardest where the cooling occurs most rapidly. A practical example of this effect would be the quenching process used to temper swords. However, this grain does not occur when the hot material cools slowly and evenly, such as with hot-rolled steel or air-cooled lava flows. A practical example of this would be the process of annealing metals in ceramics, specifically to prevent cracks and weak spots. So what you're saying is, if these basalt columns were once a very hot liquid, as geologists claim, and if the surface of this liquid were cooled under the correct conditions, you're saying the columns would develop a grain just like we see in other hard materials when they're rapidly cooled? But how can we tell if basalt columns really do have a grain? Well, materials that have a thermal grain tend to shear perpendicular to the surface that was cooled most quickly, and fracture parallel to that cooled surface. This is a result of the fact that tempered materials become progressively less hard the farther away you go from the cooled surface. As a rule of thumb, remember, layers of consistent hardness tend to stick together, whereas layers of different hardness will fracture where the difference in internal hardness is the most extreme. Not only do we see this occurring as the columns break on their own, but we can test for a grain by intentionally cracking these rock formations. If the grain is present, we should see that basalt flow rock breaks along the same axes most of the time. We can also reveal the presence of a grain when we try to split the rock. We would expect it to shear parallel to the long sides of the column, but just to be sure, let's test this claim. Here we can witness the process of splitting a rock using explosives, or specifically, splitting a basalt column. Because the explosives are placed down into a cylindrical bore, pressure from the explosion will be symmetrical, which means the rock will break along its weakest point, its own natural grain. Incredible. Observe how evenly the rock splits. Let's take another look. When the explosive is detonated, we can see the rock splits in a very even line. You can also see how the shear line is parallel to the sides of the column. So what does this mean? It demonstrates that the column has a grain, and it splits just as predicted by our current understanding of the material sciences. But this isn't the only way we can see this phenomenon take place. We can also observe this occurring when we split the basalt column with even pressure. These columns will still shear mostly along the tempered axes.
Wait a minute.
Basalt columns have an extremely hard composition compared to other common forms of rock. They have a very even color and consistent hardness. Many columns share a strikingly similar chemistry to molten lava flowing from active volcanoes to this day, but most interestingly, the way they crack reveals a structural grain known to form when hard materials are put under thermal cooling stress. Nevertheless, as we look at these pictures, it's still hard to believe something which looks so much like a giant tree stump might just be an ancient lava flow. So let's dig a little deeper and see if the famous hexagonal structures which form some of these monoliths really could have been caused by giant tree fibers. Today we find that these formations are made of rock. If they were trees in the past, there are a few ways they could have become hard as rock. Since columnar basalt is such a hard, dense material, we'll have to go on a hunt for evidence of organic matter that has become as solid and uniform as columnar basalt. Since organic matter is not made of rock while it's alive, it will have to undergo a transformation to become rock. There is one process we know of which can produce this phenomenon. It's called petrification. In order to properly address these basalt columns and mesas are giant tree stumps theory, supposing it's true, we have to consider two possibilities. One, the trees were petrified in the most common way, by near complete replacement of all original organic matter with minerals, or solid basalt in our case. And two, the elements the tree was made of helped in the petrification process, and ended up in the materials we see today. If these rock formations were living organic structures at one time, is there any evidence that plant material can petrify in the form of basalt? Unfortunately, it appears not. After many hours of research, we couldn't find even a single example of any petrified samples with a contingent structure like that of basalt. Furthermore, we couldn't locate a single example of any petrified samples that had a chemical composition similar to or even close to basalt. See, it turns out that nearly every petrified sample with public chemical analysis records we could find demonstrates that silica accounts for over 90% of the mass of petrified wood. That's a real problem for the giant tree theory when you realize basalt seldom contains more than 60% silica. In fact, it's the lack of silica that gives basalt its unique structural properties and ability to flow so quickly as a molten liquid. But what about the other consideration, that these ancient trees were silicon life forms? Would that make it more likely they could have been petrified this way? Unfortunately, no. During the process of petrification, it's true that some of the original organic matter remains behind and becomes petrified as well. The trouble with that claim is, if they were silicon trees instead of carbon trees, the silica content of the resulting petrified stump would be even higher than that of carbon-based trees, not closer to the basalt chemistry of these rock formations. As you can see, the giant trees theory is quickly falling apart. Fine, whatever, but there's still one big problem that hasn't been addressed. Here it goes. Explain why trees have fibers with this hexagonal structure. That must at least be weak supporting evidence, right? Well, it might be good evidence, if it were true. Because it turns out that tree fibers look more like cracked mud or salt pillars than columnar basalt. Thus, we researched again for quite some time looking for any plants which have a regularly hexagonal vascular structure, and to our surprise, we again found almost nothing that matched. Some plants have a semi-hexagonal vascular structure, but even the very best examples were highly irregular in shape and number of sides. Let's take a look at some of the best examples we could find of hexagonal fibers in biological material. The real problem is, there are just too many columnar basalt flows that can be proven not to be tree stumps or roots. This is because there are numerous locations where basalt columns have perfectly formed between layers of solid basalt rock. Many basaltic flows can be found in structures and locations where there are clearly no possibility of roots burrowing through. Now let's take a close look at these structures. It is well known how they form. Look at that solid block of basalt on top of the columns. That is in fact hundreds of feet of solid rock both above and below these columns. Many of these trapped columns identically resemble the size and shape of the columns that form Devil's Peak, Giant's Causeway, and many other famous flows. Just to be clear, we're not claiming that there were never giant trees on Earth. There very well could have been. We're just explaining why the claim that basalt rock formations and mountains being giant trees simply isn't factual. Our eyes can tell us a lot about the world, but they can't tell us everything. To see the whole picture, we use the tools of science and make accurate measurements to unveil the truth. In all honesty, I want to believe that this, my very own planet, had such incredible monoliths reaching towards the heavens. But I have to go where the evidence takes me. I will miss you, idea of giant earth trees. I will miss you. But hey, if you've got other evidence we didn't cover in this video, we'd love to hear about it. Please leave a comment below. I'm still hoping that someday we will find evidence these giant trees really existed. Until then, if you like what you've seen, please be sure to subscribe, and if you didn't, please let us know why in the comments.